Hi guys, welcome you to my YouTube channel, Learning Physics with IBM. And today I would like to take you to solve the past paper questions. I'm solving May-June 2023 papers, and this is going to be paper 2-3. My name is IBM, and I would like to take you to the question paper. So this is the question paper. And without wasting time, I want us to solve it. So this is a 970223. May, June 2023. The paper is 1 hour and 15 minutes. Of course, my name is IBM and I'm based in BSU. The school is called BSU. It is a British school, so it's a British school in Asia. So without wasting time, I would like to take you to the questions. Let's go to question number 1. A well has a depth of 36 meters from ground level to the surface of the water in the well, as shown in the diagram. A student wishes to find the depth of the well. The student plans to drop a stone down the well and record the time taken from releasing the stone to hearing the splash made by the stone as it enters the water. So it means the stone is going to move for a time t, but again, if he's relying on the sound, then the sound will have to travel back. So the total time will be the time for the stone to reach the surface plus the time for the sound to reach the child. So that would be the correct time this child would record. The time for the sound to reach him. So assume that air resistance is negligible. So if air resistance is negligible, acceleration is going to be g. We can use the equations of motion. Calculate the time taken for the stone to fall from ground level to the surface of the water. So using S equals to ut plus a half at squared. It is released from rest, initial velocity is going to be 0. So it is going to fall a distance of 36 meters. So I'll simply say 36 is equal to a half times acceleration, which is 9.81, then times t squared, meaning t is going to be the square root of 2 times 36 divided by 9.81. So I'll press my calculator. 2 times 36 divided by 9.81, and then I get the root of the answer. So that is 2.7. So the answer here is going to be 2.7 seconds. The time recorded by the student using a stopwatch is not equal to the time in A. So the time recorded is not by the stopwatch is not equal to the time. In fact, the time recorded by the stopwatch is going to be greater than the time we have calculated in A, because in A we just calculated the time to reach the water surface. But remember, the student must hear the sound that the stone has hit the water surface, so the sound must move backwards. So the time recorded by the stopwatch is the time to reach the water surface plus the time to return to the student. So suggest 3 possible reasons other than the effect of air resistance for this difference. So there are several reasons. I will state a few of them. Number 1, you could mention reaction time between hearing the splash and stopping the stopwatch. So you can say reaction time. Reaction time between hearing the splash and stopping the stopwatch. So the student must hear the splash before he stops the stopwatch. So there's that time lag between hearing and stopping. That is the reaction time. Number 2, I will list them, and I will not follow the lines given here. It is impossible to release an object without adding some force. So it means the object may have been given some initial velocity. So the stone must have been given some initial velocity. The stone must have been given some initial velocity, which would mean that initial velocity is not zero. So initial velocity would not be zero. It is impossible to release an object without adding some force onto it. So that means it could have been given some initial velocity. Number 3, the stone may not be falling vertical downwards, may be falling at an angle to the vertical. So that means it would affect the results. So the stone does not fall exactly vertically as it is assumed. So the stone does not fall vertically as it has already been assumed. So that is number 3. Another one, maybe there is a difference in the value of g that we have used for that particular time. So we call that local value of g. At that point may not be exactly 9.81. So the local value of g at that point may not be exactly 9.81 meters per second squared as we have assumed, because g varies, g slightly varies from one point to another. So the local concentration of the local value of g may not be exactly the one we have used. Number 4, maybe the stopwatch has a zero error. The stopwatch could be having a zero error, has a zero error, or it may not be properly calibrated, or may not be properly calibrated. So that affects the value of time. Also, we could think of the student may not let go of the stone from the ground, from exactly the ground level. Student may not let go of stone from the ground level, which would mean the value of t may either be higher than expected or lower than expected, because the height may not be exactly 36 meters as it is assumed. Also, the sound of the splash takes some time to reach the student, and it has not been taken into consideration. The sound of the splash takes some time to reach the student. The sound of the splash takes some time to reach the student, which has not been accounted for. So in calculating the time, we do not account for the fact that the sound will also take some time to reach the student. And maybe the student may not let go of the stone and start the stopwatch at the same time. Let me put this one here. The student may not let go of the stone and start stopwatch at the same time. It's hard to let go of the stone and start the stopwatch at the same time. This is going to automatically affect the value of time. Okay, so you just need the 3. Me, I just had to write many. The student repeats the experiment 3 times and uses the results to calculate the depth of the well. The values are shown in the table. The true depth is 36.0 meters. Explain why these results may be described as precise but not accurate. So 54.4, 53.9, 54.1, they are almost varying in only the last digit. So they are precise but not accurate. The accurate value should be 36. So precise, we can say they are precise because the results are close together. Results are close to each other. In other words, the results have a small range. Then not accurate. Let me first check the percentage. So the percent, I'll just take one value, 54. Let me check the average anyway, 54.4 plus 53.9 plus 54.1 divided by 3. The average is 54.13. 54.13 is the average minus the expected value 36.0 divided by the expected value, which is 36, times 100. I just want to find percentage difference in the values. So minus 36 divided by 36 times 100, it's almost 50%. So the values are not accurate because the percentage difference from the expected value is about 50%. So the average of the values is about 50% different. Different from the true value. So the average of the values is about 50% different from the true value of the expected value. So they are not accurate. Not accurate, but precise. The sphere floats in equilibrium. If it is in equilibrium, the resultant force is 0. On the surface of the water of density 10, 50 kilograms per meter cubed as shown, 21% of the volume of the sphere is below the surface of the water. So let the volume of the sphere be V. And 21% is going to be 0.21 times V. Okay. So when it is in equilibrium, of course, the force is acting, its weight is acting downwards, and then the upthrust is acting upwards. So if it is in equilibrium, the upthrust is equal to the weight on the surface. That means the resultant force would be 0 because the resultant force is supposed to be the weight minus the upthrust. So calculate the density of the sphere. So first of all, if it is in equilibrium, we know that the upthrust is equal to the cross-sectional area times difference in pressure, which is going to be the cross-sectional area times the density of the liquid in which it is floating times G times a difference in H. But A and the cross-sectional area is going to be the volume. So this is going to be equal to density of the liquid, G times the volume of the liquid it displaces. But they say 21% of the volume of the sphere is below the surface of the water. That means the volume displaced of the liquid is 0.21 V. So this means the upthrust is going to be the density of the liquid, which is 10, 50, times G, which is 9.81, times the volume of the liquid displaced, which is 0.21 times capital V. So that is the upthrust. But then the weight of the sphere is equal to the mass of the sphere times G. And the mass of the sphere is the density of the sphere times the volume of the sphere, which is capital V, then times G. So these two quantities should be equal. So density of the sphere is not known, times V, then times 9.81. So I'm just going to combine these two equations. For equilibrium, the upthrust is equal to the weight. So it means density of the sphere times the volume of the sphere times 9.81 should be equal to the density 1050 times 9.81 times 0.21 times V. So V cancels out and I get the density of the sphere. 9.81 also cancels out. So I'll just have 1050 times 0.21, which is 220. So density of the sphere is 220. So this is 220. The sphere is now held so that its entire volume, the whole volume V, is below the surface of the water. The sphere is then released, capturing the initial acceleration. So if it is now entirely into the water, if there's an acceleration, the resultant force acting is going to be the upthrust minus the weight. Because when it is now held so that its entire volume is below the water, the upthrust increases. So it's the upthrust which causes the resultant force upward. So the resultant force is equal to upthrust minus weight. Resultant force is mass times acceleration. This will be, of course, the mass of the sphere. Okay. And we know that the mass of the sphere is equal to the density of the sphere times the volume of the sphere. So that is the mass of the sphere. So let's just substitute. The resultant force is the mass of the sphere, which is equal to density of the sphere, which has been got as, okay, mass of the sphere times, density of the sphere mass of the sphere is density of the sphere times the volume, then times the acceleration should be equal to the upthrust. The upthrust is going to be the density of the liquid times G times the volume of the liquid. Of course, if the entire volume of the sphere is in the water, it means the volume of the water displaced is still the same as V. Then minus the weight. The weight of the sphere is equal to the mass of the sphere, which is density of the sphere times its volume, then times G. So the density of the sphere is 220, its volume is V, acceleration is A, the density of the liquid is 1050, then times G, which is 9.81, then times V, then minus the density of the sphere, which is 220 times V times 9.81. So V cancels out because it's everywhere. V cancels out. So the acceleration is going to be 1050 times 9.81 minus 220 times 9.81 divided by 220. So 1050 times 9.81 minus 220 times 9.81, then divide by 220. So this is giving me 37. So this is going to be 37 meters per second squared. Okay, 37. The sphere accelerates upwards. The sphere accelerates upwards. But remains below the surface of the water. Let me explain what happens to the acceleration of the sphere as its velocity begins to increase. So this is the sphere. It is accelerating upwards. So motion is upwards. This is motion. Of course, we also have upthrust, which is upwards. We have the weight, which is downwards. If it accelerates upwards, it means the dragger force is also downwards. The dragger force is the frictional force. So what happens then? The resultant force is going to be equal to, because it goes upwards, is the upthrust minus the weight plus the dragger force. So, and remember, the resultant force is equal to the mass times acceleration. So as the velocity begins to increase, the dragger force increases in the opposite direction. So the dragger force increases, meaning that this sum becomes bigger, but there's subtraction here. That means the whole of this becomes smaller. So the resultant force decreases, and when the resultant force decreases, the acceleration also decreases. So it means the acceleration is tending to zero. So finally, the speed will become constant. So we shall simply say that the viscous drag increases with the speed or with the velocity. The viscous drag increases with the velocity, so the resultant force decreases. Resultant force decreases. And as the resultant force decreases, remember the upthrust and the weight remain constant. Upthrust and the weight stay the same. The upthrust and the weight stay the same, so it means the acceleration decreases. So the acceleration decreases as its velocity increases. So the acceleration will be tending to zero as velocity increases until a point where the velocity remains constant and the acceleration will be zero. That will be called terminal velocity. Sorry. Okay. State the principle of conservation of momentum. Of course, we know that the total momentum of an isolated system of interacting bodies is always constant. Total momentum of an isolated system of interacting bodies is always constant. A firework is initially stationary. That means total momentum initially is zero. It explodes into three fragments A, B, and C that move in horizontal plane as shown in the view from above. Okay. So before we do this, we can solo resolve this in the horizontal and in the vertical. In the horizontal, it is going to be V sine theta if we use theta, and here it will be V cos theta if we use theta. Fragment A has mass 3m and moves away from the explosion at the speed of 4 meters per second. B has mass of 2m and moves away with 6 meters per second at right angles. Fragment C has mass 3m and moves at speed v and at an angle theta as shown. Calculate the angle theta. Okay, so we are going to conserve momentum in the horizontal and in the vertical. When I write px, I'm meaning momentum in the horizontal. So 0 is the total momentum in the horizontal. But after collision in the horizontal, we have momentum of this one to the right hand side and momentum of this one to the left. Momentum this side will be m times v sine theta. Momentum the other side is 3m times 4. They're in opposite directions, so one must be positive. So we shall say 3m times 4 plus negative mv sine of theta. In other words, we can simply say that v sine of theta is equal to 3, because m cancels out. So this is going to be equal to 12. That is one equation. Then I consider momentum in the vertical. Total momentum before is still 0. But in the vertical, m moves downwards. In the vertical, it will be mv cos theta. And upwards, we have 2m times 6, and they're in opposite directions. So one must be positive, one must be negative. So this will be equal to 2m times 6 plus negative mv cos theta. M cancels out. So we remain that v cos of theta is 2 times 6, which is equal to 12. So this is equation number 2. So when I say equation number 1 divided by equation number 2, you get tan theta. V cancels, sine theta divided by cos theta is tan theta. So tan theta is equal to 1. So what is theta? Theta is going to be the tan inverse of 1, which I think is 45 degrees. So theta is going to be 45 degrees. Then the speed v. So since theta is 45 degrees, so it is easier for us to find the speed v. You can just take any equation which has v. So I could simply say v sine of 45 is equal to 12. So v is equal to 12 divided by sine 45. So 12 divided by sine 45. So that is 16.97, approximately 17. So this is 17 meters per second. Alternatively, you could find, you could use the resultant of these two momentum, this side. Find out this momentum and this one. The resultant of these two to the other side would be 2 times 2m times 6 but squared plus 3m times 4 but squared under the square root. That would be the resultant that side. And the resultant this side will simply be m times v. If I use this, and they're in opposite direction, so they should be equal. So I will simply say mv is the same as the square root of 2m times that. I think that is 12m, but this is squared, plus 12m, which is also squared. When I remove the square root, I have that m squared v squared is equal to 12 squared m squared plus 12 squared m squared. So m squared cancels out. So v squared would be the square root of 12 squared plus 12 squared, that is 200 and, so v, when I remove the square root, v is going to be the square root of 12 squared plus 12 squared, that is 288. Let me check. V root of 288. It is 17, so this will still give us 17 meters per second. So that could be another way of doing that. That is, I've used momentum on one side equal but opposite to the momentum on the other side. Okay. The firework in B contains a chemical that has a mass of 5 grams and has a chemical energy per unit mass of 7 joules per kilogram. When the firework explodes, all the chemical energy is transferred to kinetic energy, or the chemical becomes kinetic energy. Show that the total chemical energy of the firework is 3.5. So it is very simple. Chemical energy is going to be the mass, which is 5.0 times 10 power negative 3. This is kilograms times the mass of the energy of each kilogram, which is 700 joules. We can check with our calculator. 5 or 700 times 5 exponent minus 3. So that is 3.5. Calculate the mass m. So since all the chemical energy is transferred to kinetic energy, so we know that kinetic energy is a half m v squared. This should be 3.5 joules. So I'll say 3.5 equals to a half times m times v. Now this was the firework in B contains a chemical that has mass 5. All of the chemical energy is transferred to the kinetic energy of the fragments, okay, for all of them. So for the first one, it is 3m times its speed was 4 squared plus. For the second one, it is a half. Its mass is 2m. Its speed is 6 squared. And the third one is going to be a half. Its mass was m and its speed is 17 squared. We've got it as 17. So I'll just press my calculator. 3.5 equals 2. So we have 3 times 4 squared divided by 2 plus that is 6 squared plus 17 squared divided by 2. 17 squared divided by 2. So that is 204.5. So this is 204.5 m. So I divide to find m. M will be 3.5 divided by 204.5. So 3.5 divided by the answer, that is 0.017. 0.017 kilograms. So that is the mass. For a progressive wave, state what is meant by frequency. Of course, frequency is the number of oscillations of the source per unit time. The number of oscillations of the source or of a point on the wave source, or it can be a point on the wave per unit time. So that's what we call frequency. Remember, the frequency of a wave depends on the source. So the number of oscillations which a source makes is the number of waves that we observe. So that is why we define frequency as the number of oscillations of the source per unit time. A loudspeaker, microphone, and cathode ray oscilloscope are arranged as shown here. The loudspeaker is emitting a sound wave which is detected by the microphone and displayed on the screen, the CRO as shown. The time base of the CRO is 0.50 seconds, so I'll call that one X. The Y gain setting is that, so I'll call this one Y. Okay. Calculate the frequency of the sound. First of all, we shall find the period from the length representing the cycle times the time base setting. Which length represents the cycle from the graph? So if we start from here, one cycle stops here. This is 1, 2, 3, 4 centimeters. So L is 4 centimeters. So this is going to be 4 centimeters times the time base setting, 0.5 milliseconds. So times 0.5, because it is in milli, I'll say times 10 power minus 3 seconds per centimeter. So per centimeter cancels with that. Then it means frequency is equal to 1 over period, which will be 1 divided by 4 times 0.5 times 10 power minus 3. So we can check this with our calculator. 1 divided by open brackets 4 times 0.5 exponent minus 3. So this is giving me 500 as the frequency. So this is 500. Then the amplitude of the signal, the amplitude capital M, or the amplitude, is simply going to be the length representing the amplitude times the y gain, or the y setting. What length represents the amplitude from the graph? So from the amplitude is 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. How many squares are those? 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So the number of small squares here are 14. 1, 2, 3, 4. 14 small squares times 1 small square. 1 square is equal to 1 over 5, which is 0.2. Now there are 14 small squares, so I will say 14 times 0.2. 14 times 0.2. So this is 2.8 centimeters. So the length representing the amplitude is 2.8 centimeters. So I'll say 2.8 centimeters times the voltage setting, or the Y gain setting, which is 0.2 volts per centimeter. So times 0.2 volts per centimeter. So this cancels. And I think this gives us times 0.2. That gives us 0.56. So V is 0.56. Then the intensity of the sound wave in B is reduced to a quarter. Intensity is reduced to a quarter, okay, of its original intensity. So let the original be I. So the new intensity is going to be a quarter of I without changing frequency. So the period is the same. Assume the amplitude of the signal received by the CRO is proportional to the amplitude of the sound wave. Sketch the trace that is now seen on the screen. So we are going to sketch here. Intensity is directly proportional to amplitude squared. We know that. So for the first one, let's say the intensity I is equal to constant times the amplitude, which was 2.8 centimeters, or which was represented by 14 small squares. So that is 2.8 centimeters. Then for the second one, the intensity I is equal to a constant times the amplitude which we want to find. Remember, this was squared. So I'll divide the two equations. Remember, I2 is a quarter of I. So when I divide a quarter of I divided by I is equal to K S squared divided by K 2.8 squared. So K cancels, I cancels. So it means S squared is going to be equal to a quarter times 2.4, which is 2.8 squared divided by 4. When I find the square root, it means A is the square root of that one, which will be 2.8 divided by 2, which is 1.4 centimeters. So the new amplitude is going to be 1.4 centimeters. In other words, it will be a half of the other one. The other one was represented by 14 small squares. This will be represented by 7. So 1, 2, 3, 4, 5, 6, 7. To start from here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I'm now sketching my curve. Remember, it was the same frequency. So they would meet at in that horizontal line. So they should meet here. They should meet there because the frequency is the same. That will be our new curve. You should draw a better curve than mine, but that is how it's going to be like. Okay, yeah, that took much time, but it's worth it. Another waves equation. A metal sheet is now placed in front of the loudspeaker in B as shown in the figure. So they have now put a metal sheet. Of course, there is going to be reflection. So the principle of superposition. Of course, we know for superposition, when two or more waves meet, when two or more waves meet at a point, the resultant displacement is the algebraic sum of the individual displacements of the waves. Okay. Then the initial position of the microphone is such that the trace on the CRO has amplitude minimum. An amplitude minimum, of course, that is going to be a node. Point of zero displacement. It is now moved a distance 1.5 meters. So we are starting from here where we have a node. Then we move a distance of 1.505 meters away from the loudspeaker along the line joining the loudspeaker and the metal sheet. As the microphone moves, it passes through three positions where the trace has amplitude maximum before ending at a position where the trace has amplitude minimum. So here we have another node, amplitude minimum. So there should be three antinodes in between. So 1, 2, 3. Of course, between every two antinodes, there must be a node. So there must be a node between every two antinodes. Okay, determine the wavelength of the sound wave. So the distance from the starting point here to this point was 1.05 meters. So you see that this is a half plus a half plus a half. It means the length of between the 2 points is giving half plus a half plus a half. Those are three halves. So that is 3/2 of wavelength. So um, the length L is going to give us 3/2 of wavelength. So the wavelength is going to be 2L divided by 3, which will be 2 times 1.05 divided by 3. 2 times 1.05 divided by 3. So this is 0.70. So we shall write 0.70 in meters. Use your answer in B Roman 1 and B Roman 2 to find the speed of the wave. You know that speed is equal to lambda times f. In Roman 2, we have got the wavelength as 0.7. And in Roman 1, we got the frequency. B Roman 1, we got the frequency. The frequency was 500. So we shall simply say times 500. So this is times 500. And when I press my calculator times 500, it is 350. So this is 350 second. Okay, we move to electricity, I think. Yes, here is electricity. A student sets up a circuit with a battery, an ammeter, a heater. I think a heater is represented like this. And light dependent resistor, and I think an LDR is represented like this. The battery has negligible internal resistance. A voltmeter is connected across the heater. On the circuit, on the figure, complete the circuit. So I think this is easy. So we shall just draw a heater in series with a fixed resistor, with the LDR. So this is the heater, and this is going to be the LDR. There is no any other component here. There is no switch, so I'll just join this to this. Then the voltmeter is connected across the heater, so I'll put here the voltmeter. So that will give you 3 marks. That will give you 3 marks. The heater is a wire made of resistivity 1.1 times 10 power minus 6. The wire has length 2 meters, cross-sectional area 3.8 times 10 power minus 7. The reading of the voltmeter is 4.8 volts. So this is the PD across the heater. Calculate the resistance of the heater. So we know that resistance is equal to rho L over cross-sectional area, where rho is resistivity. So this is going to be 1.1 times 10 power minus 6. L is 2.0 meters divided by cross-sectional area, which is 3.8 times 10 power minus 7. So I'll just press my calculator. 2 times 1.1 exponent minus 6 divided by 3.8 exponent minus 7. So this is 5.78. The whole decimal number is recurring, so I'll just write 5.8. So this is 5.8 ohms. Then the reading of the ammeter, that is the current. The reading of the ammeter, that is the current. So current is equal to V over R. Current is equal to V over R. Oh, there's an ammeter here. A student sets up a circuit with a battery, an ammeter, a heater, LDR. Sorry about this. I must add an ammeter here. Of course, the ammeter must be in series. Yes, the ammeter must be in series. So that one, the ammeter was missing there. So the reading of the ammeter is current. So V is 4.8. The PD across the heater is going to give us the current through the whole circuit, because they're in series, the current is the same. So divide by the resistance of the heater, 5.8. So 4.8 divided by 5.8. So that is 0.83. So the ammeter reading is 0.83 amperes. The heater is replaced by a new wire. The heater is replaced by a new wire. The new wire is made of the same metal. That means it has the same resistivity as the wire and same length, but larger diameter. So same metal, that is same resistivity, same length L, but larger diameter. Remember, diameter will give us cross-sectional area, and the area is pi d squared over 4. So it means the area is directly proportional to diameter squared. And from resistance is equal to rho L over area. We also notice that resistance is inversely proportional to area. The rho and L are the same. So a larger diameter means a larger area, which means the resistance decreases. So we can say area is directly proportional to d squared, and d is larger for the new wire. For the new wire, so A is larger. Area is larger, but we know that resistance is inversely proportional to area. So R is less. So the resistance is going to be less than that of the first wire. State and explain whether the new reading on the voltmeter is greater than, less than, or equal to 4.5, 4.8. So here we have the heater and we have the LDR. Of course, we had the ammeter, we had the power supply, the battery, and we had the voltmeter here. So we notice that because the resistance of the new wire is less, it means total resistance is going to be lower. And if total resistance is low, it means total current is going to increase. Total current is going to increase. So if total current increases, yet the resistance here is smaller, the EMF, the value here V should be equal to V1 plus V2. So V is going to be V1 plus V2. Since the current has increased, it means since the current has increased, it means the PD across V1 has increased because the current has increased. And remember, for V1, the resistance is the wire has a smaller resistance, total current has increased. Okay, if the total current has increased, but the resistance of V1 has decreased, and the same current is going to go through the LDR, so it means V1 is going to decrease, and since total should remain V, it means V2 should just increase. Therefore, we are saying total resistance decreases, total resistance decreases. Total resistance decreases, and if total resistance decreases, it means the current in the circuit increases. So the current in the circuit increases. Remember, it is the resistance of the heater which has gone down, but the current has increased. So it means the PD across the heater goes down, which means it should be compensated by the PD across the LDR going up. So meaning PD across LDR increases. So the voltmeter reading is less, or it decreases. It is going to be less than 4.8 volts. Because the current has increased and the resistance of the LDR has remained the same, it means the PD across the LDR is going to be greater. So that means to maintain the same total EMF, the PD across the heater is going to be smaller, so it is going to be less than 4.8 volts. Okay. Define the Young modulus. Of course, Young modulus is simply stress divided by strain. Stress divided by strain. You don't need to write a story. A uniform wire is suspended from a fixed support. Masses are added to the other end of the wire as shown in the figure. The variation of the length L of the wire with the force F applied to the wire by the masses is shown in the figure. So L against F. The cross-sectional area of the wire is 0.95 millimeters squared. Determine the unstretched length. So when force equals to 0, then L is going to be the unstretched length. There is no force, but there is a length. So this is going to be the unstretched length. So when F is 0, the unstretched length is going to be 1.998 meters. For an applied force of 30 newtons, determine the stress. Of course, we know that stress is equal to force over area. The force is 30 newtons. the area was given as 0.95 millimeters squared. I have to change this area into meters squared. I think this will be 0.95 times 10 power minus 6 to change it to meters squared, because 1 meter is 1,000 millimeters. So if this is squared, the other one is also squared, so that is power minus 6. So this would be 0.95 times 10 power minus 6. That is the area. So this would be 30 divided by 0.95 exponent minus 6. So this is 3.2 times 10 power 1, 2, 3, 4, 5, 6, 7, power 7. 3.2 times 10 power 7 pascals. Then the strain, we know that strain is equal to extension over the original length, or the unstretched length. The extension for 30 newtons is 2.003 minus 1.998. It is 2.003 minus 1.998 divided by the unstretched length, which is 1.998. So 2.003 minus 1.998 divided by 1.998. So this is giving me 2.5 times 10 power minus 3. 2.5 times 10 power minus 3. So that is the strain. Lastly is particle physics. The table shows incomplete data for 3 flavors or types of quarks. The elementary charge is E. Complete the table by inserting the missing charges. Of course, we know that any word which is used as the name of a quark, but when the word has a pleasant English meaning, the charge is plus 2 over 3e. So for charming is something good, so the charge is plus 2 over 3e. The e is already given there, I will not add it in the table. Then down, any word which has an unpleasant meaning in English, but representing the name of a quark, the charge is minus 1 over 3. So this is minus 1 over 3 times that e. Then the antiquarks have just opposite charges. So this is minus 2 over 3e plus 1 over 3e minus 2 over 3e. Use the symbols given in the table. Using symbols given in the table, state a possible quark combination for the following hadrons. A neutron, of course, a neutron has 3 quarks. A baryon has 3 quarks. A neutral baryon. Remember, baryon has 3 quarks, but it is neutral, so it should have charge 0. The charge should be equal to 0. So just look here and see which combination gives you charge of 0. Plus 2 over 3. When I add all 2 downs plus 1 up, that is 0. So you could say up, down, down. Or you could say using the symbols given in the table. So I can just say up, down, down. You could say charm, down, down. I think that is all. If I use the symbols given in the table, up, down, down, or charm, down, down. Yeah, one of those. Then a meson is a quark plus an antiquark, and the charge is positive E. We want a charge of positive E from a quark and an antiquark. When I add up and ant up, the charge is 0. Up and ant down, the charge is positive E. So we have up and ant down. So I can also have charm and ant down. Then quarks are fundamental particles. Electrons are in another group of fundamental particles. State the name. Of course, electrons are called leptons. Electrons are called leptons. State the name of another particle in this group. Of course, the leptons, we have positrons, we have the neutrinos, and we have the antineutrinos. You just state one. They said state the name of another particle, just one. And the antineutrinos. So one of those, or these ones are called leptons together with the electron. I think that marks the end of this paper. I tried to keep time. I have a balance of around 15 minutes. I think you have learned something from this. And until next time, bye bye.